Okay, oscillations. Introduction to oscillations. It's actually pronounced oscillations, but I think it's funny to say oscillations. I also think it's fun to say knigget. It's not the horse in chess, it's the knigget. Yeah, it's the knigget. The knigget. Okay, so oscillations. Here is actually a topic to start off with. I'm introducing you to one of the major systems that we're going to give as an example. I've got two classic examples of things that oscillate, although as I just referred to, there are a billion. And the graph that results if you track how this thing moves back and forth. So take a look. This isn't just an intro slide graphic. This is actually a topic here. Foist off. The thing. I have a box. I have a spring. I'm not going to do the pen, pineapple, apple, pen dance. If I attach a box to a spring and let it vibrate, bounce, wiggle up and down, that's an example of what I call a simple harmonic oscillator, SHO. You'll see references. I'll refer to SHO all the time here. Simple harmonic oscillator. Something which bounces up and down, not just in any old way. This is not an oscillation. I may be jumping up and down. I might be jumping up and down with a repeating time, a repeating pattern, a period, but I'm not sinusoidally oscillating. A mass on a spring vibrates up and down in a particular pattern. If you're to graph its position versus time, it graphs out a sine wave or a cosine wave, depending on where you start. That's what I mean by simple harmonic oscillator. Simple harmonic oscillator is one that wiggles back and forth, and not just wiggles back in any old way, wiggles back and forth sinusoidally. So, classic example numero uno, box on a spring. Tomorrow, not tomorrow, class tomorrow, Wednesday, we'll talk about how a pendulum is another example of this. A grandfather clock. A kid on a swing is another example of something which is a simple harmonic oscillator. Okay, here's a sine wave. Here's a graph of sine. Everyone has seen sine and cosine, right? For my perspective, those are the same graph. I'm going to refer to sine waves and then write down y equals cos x. And those are the same thing for me. What's the difference between sine and cosine? The only difference between sine and cosine is one starts at the midpoint and one starts at the peak. From the perspective of the physics underlying the motion of an object, saying, well, let's go to the kid on the swing example. If I hold the kid on the swing back and at time 0 release the kid on the swing, then that's a cosine function, right? They're starting at the peak. At time 0, they have max amplitude, cosine. There's no physics difference between that and if I release them and then start my timer, say time equals t equals 0 when they're swinging through the midpoint, when they've got a sine shape starting at the origin going up. Okay? So if I say sine wave, you have to determine in any given problem, am I looking at sine, starts at 0 going up, or am I starting at cos? Am I using the function cosine? Starts at max, starts going down. For any given problem, do not just plug in sine because I say sine wave. You have to think, am I starting at max? Cosine. Am I starting at middle? Sine. Regardless of where I start, we refer to the distance from the midpoint to the peak, the amplitude of the function. I said it twice. We refer to the measure from the midpoint to the peak as the amplitude of that graph. Now remember what did we just do last week with RMS? Remember RMS voltage? That's not from midline to peak. That's a 0.707 times that amplitude. When I talk about amplitude in alternating current, in AC, RMS is an important measure. We're never doing RMS when we're talking about swings moving back and forth. There is actually a good, useful meaning we can assign to RMS amplitude of a swing or a mass bouncing back and forth on a vibration if you want to talk about the energy behind it, but I'm calling that beyond the scope of the class. So for our purposes here, if I say amplitude in here, you can think of it only as the peak amplitude. I want to emphasize also period, just like before. A period is the time between equivalent points on a cycle. If you look at the time from a peak instant to a peak instant, that's a period. If you look at the time from a trough instant to a trough instant, that's a period. If you look at the time from crossing zero going up, to a crossing zero going up, that's also the period. Are you guys, I feel like we've talked about period and frequency a fair number of times. Does everyone really feel happy with what frequency measures, with what period measures? Great. Then here is, on this graph, a fair fraction of what I want you to know for this. I want you to know that you can make a graph of a, in this case, displacement versus time, where the pendulum bob, where the mass on a spring is. This can be graphed out as a sine or cosine wave. We need to be able to measure the amplitude and period. And if all y'all's nodding along is in fact correct, you guys are comfortable with if I give you a period, you can find a frequency and vice versa, yes? Then that's a lot of what we've got. Great, you're in good shape. Now, I said not everything makes a sine wave, not everything makes simple harmonic motion. I'm going to say simple harmonic motion. The physics of oscillations, we're going to focus on things that repeat sinusoidally. There's a physics constraint on that. What makes sine motion is a linear restoring force. This is a test question. I will quiz you on this. Not quiz. Well, probably both quiz and midterm you. Final exam you. What kind of force causes a sinusoidal motion? A linear restoring force. What do we mean by linear restoring force? Linear means if you graph it, it's a line. Wait, hold on. I thought I said if I graph it, it's a sine. Graph what? If I graph the motion, where the spring is as time passes, height versus time is a sine wave. I'm not talking about that when I say line. When I graph the force, when I graph force versus position, that is what I insist must be a line. Do you guys remember doing springs once upon a time? Force of a spring is K times X. What does the graph of y equals a constant times X look like? Bonk. Right? Straight line. Straight diagonal line. It is a linear function. When I say linear, by the way, I mean that in a very precise way. A physicist, a mathematician saying linear means the graph is a line, a diagonal, perhaps, line. So in particular, if I've got a function of the form y equals mx plus b, that can be a force of the form y equals mx plus b. That is something that could generate vibrations, oscillations, simple harmonic motion. You must be able to distinguish between these two kinds of graphs. Where is something as a function of time? That is to say, if I draw its position and how its position varies, that's a sine wave. What kind of force generates that? That's a straight line, diagonal line function, a linear function. By the way, I talk a lot about position versus time. If position's a sine wave, if you've taken calc, derivative of sine is cosine, derivative of cosine is negative sine. Velocity and acceleration are also sine waves if position is a sine wave. We'll talk briefly about those. This is not, obviously, a calc-based class, so I am not going to have you calculating derivatives and integrals explicitly, but we will use a result of calculus to get out a maximum speed and understand the difference between up and down speed and left-right speed. So, big takeaway here. First, I want you to think about what it means for motion up and down, motion back and forth, motion as a function of time, where something is and how it is moving, comes from a pushback which is linear, which is directly proportional, in fact, to your displacement from some origin. The force causes the motion. Okay, quiz yourself real fast. What function describes simple harmonic motion? Test yourself, then I want you to give me the finger. Vote. Quadratic, exponential, inverse, linear, sinusoidal. What do y'all think? Which function describes L motion? I see half of you voting choice D and half of you voting choice E. I would say the function that describes the motion is the sine wave. The function that describes the force is what the other half of you were telling me is the linear function. Again, this is cause versus effect, man. What causes the motion must be a linear function. The result, the effect of that linear function is a sinusoidal position. Please, Selena. The sine wave is the function of where you are versus time. The motion is sinusoidal if the force is proportional. Okay, let's talk about those spring forces being linear, by the way. Spring is directly proportional to your extension. That is to say, if you compress a spring twice as great, it pushes on you twice as hard. If you stretch a spring twice as far, it pulls on you twice as hard. That's what I mean by proportional. Spring force is proportional. A spring vibrates, oscillates back and forth sinusoidally. A mass will boing, boing, boing on the spring because the further it goes, the harder it's pulled. The further it compresses, the harder it's pushed. That is what is required to generate force equals mass times accelerate, generate a sine wave. You've got to push back harder the more compressed you are. You've got to pull back harder the further extended you are if you want to get a sine wave. Contrast this with, what kind of motion do we have if we've got, say, constant force? What kind of motion do you have if you've got, what's a force that's a true constant, that doesn't vary with position? A string? Sure. A string, a constant tension force. If I've got a tension force of a string, is a string going to cause a boing, boing, boing? What's another constant force? Tension could be one. Gravity, mg, that does not depend on position. Perfect example. Gravity causes things to accelerate, but they don't cause things to go up and down and up and down. There is no return back and forth with the constant force of gravity. If you even just had a constant force of gravity, which is, I don't know, have a, don't misquote me, don't go tell the dean that I said this, but if we had flat Earth, and if, on this side of the Earth is America, and on this side of the Earth is China, and people walking around with their heads upside down, and people walking around with their heads the other upside down, okay? And you cut a hole between America and China. I could imagine gravity being constant in either direction, and you could drop a stone in that hole and have it go back and forth. Does that make sense? Are you picturing this? There's a flat Earth. Gravity acts down on this side of the Earth. Gravity acts the other down on the other side of the Earth. That would not generate sinusoidal motion. A rock that you drop from above the hole to China would go down. It would speed up. It would go through the hole. In China, it would appear from coming coming from the other side, coming from the ground and going up. It would slow down, turn around, speed up, fall back through the hole to America. From here, it would go up from the surface of the ground, up, fall back to China. That would not actually be a sine wave. That would be parabolic motion. You'd have stitched on parabolas. It would not obey the function y equals sine of x. Constant functions don't get this. What's another force formula that you guys have learned? Normal force, normal force. Well, I'd say a constant force, in general, doesn't produce. What's another formula? How about maybe from this year, for this module, for this semester? Huh? QE. An electric field, say particular for the point charge model, KQ on R squared. The 1 on R squared form. That is to say that the distance between an object, 1 on that distance squared, is affects the force between two charged particles. Charged particles do not oscillate near each other. They do not oscillate sinusoidally near each other. That force formula does not give rise to vibrations. There are actually interesting vibrations in, you may learn about vibratory and oscillatory behavior for God's sake, in chemistry class. There is oscillatory behavior in molecules, and that results from a complex interplay between the electric force and quantum mechanical statistical forces. So there are vibrations that result from electricity, but only as a result of complex interplay between that and quantum mechanics. In any case, whenever we see oscillations, whenever we see simple harmonic motion, vibrations that are sinusoidal, the force that causes those has to be linear. The resulting motion is sinusoidal. Have I banged that drum hard enough? Well, drum heads are also sinusoidal, but let's move on. Okay, more terminology, and have a formula. Remember what I said before about cos versus sine. It's the same function for me. You just got to apply for yourself whether we're talking about starting at the middle sine or starting at the top cos. Simple harmonic motion can be described mathematically using a cos omega t or a sine omega t. The amplitude multiplies your cosine or your sine function. That number which multiplies cos, the number which multiplies sine, gives rise to the max deviation from the center line. Exactly like we saw in that graphic before. Here's where that comes into play mathematically. Do you have your graphing calculator, Sandy? Go graph for me. Real fast, on your graphing calculator. Graph for me. Y equals 2 sine x. Then graph for me y equals 5 sine x. What's the difference? What does it look like in those two functions? What's the max height of the first and max height of the second? And what that graph y equals 3 cos x while you're at it. You should notice a pattern here. Do you remember how to graph on your graphing calculators? Yeah. But I'll give you a second. Once you made the graphs, use the cursor to scan back and forth along it. Look for the peak height of each of these functions. So I'm hoping everyone has had a chance or has recently done this, recently enough in math class done this to know what these look like. 2 sine x, 5 sine x, 3 cos x. It's the same shape for all of these. 2 sine x goes up as high as 2. 5 sine x goes up as high as 5. 3 cos x goes up as high as 3. The number that multiplies the cosine or sine tells the maximum value of the function. And also, goes down as low as -2, goes down as low as -5, goes down as low as -3. So it's also the absolute value of the negative extent. The amplitude is the 2, the 5, the 3 in this example. Exactly. That's how you can look at a mathematical graph and deduce what is the equation that produced it. Okay, so amplitude, that which multiplies your cos or your sine equation. What about the inside of the function? By the way, I'm going to smack anyone who calls this W, which is probably about most of the class. Everyone always calls this W. It's not W, it's omega. It's omega. Omega, natural frequency. You've dealt with this variable last semester. Well, I don't know. Selena, you took from a different instructor. Did you talk about rotation way back when? Angular frequency? Yeah, we did a little bit too, and nobody liked it. Did you like it? Okay. So, once upon a time, I talked about I talked about angular frequency, radians per second. And we talked about the radians per second. Radians are another way of measuring angle. Talked about something either rotating or orbiting, circular motion in general. And omega was used as the symbol that described how rapidly angle changed. Here, the mathematics behind omega, natural frequency, are identical, except instead of describing where something is in terms of angle, we're only talking about how rapidly the sine wave is wiggling. Don't get these confused. They're mathematically, the structure is very, very similar. They're huge analogies. The units of natural frequency and the units for angular frequency can be analogous. We could talk about them in terms of radians per second. Angular frequency, where is something? Angular velocity, where is something around a circle? Natural frequency, omega, radians per second, where is something along a sine wave that is not necessarily moving in a circle? Talk more about that when I can draw again when I can draw sketches on my paper. Okay, there is a connection. Don't get them confused though. If you see references, natural frequency is also sometimes called angular frequency. If I just say frequency, I'm talking 1 over period. If I say natural or angular frequency, I'm talking about omega. You all have your graphing calculator still handy? Real fast for me, I want you to do something. I want you to graph 3 more functions, y equals sine x, y equals sine 2x, and y equals sine 5x. Wait, don't hit enter. What do you think these are going to look like? Turn to your neighbor and make a prediction. What do you think the difference is going to be if you graph y equals sine x, y equals sine 2x, and y equals sine 5x? What do you think it'll look like? Make a prediction. Okay, do it. You made your prediction. Graph it, baby. Sine x, sine 2x, sine 5x. What is the effect? You may have learned this in pre-algebra once upon a time. What is the effect of multiplying the independent variable. What does that do to a graph? If I multiply the x in any function whatsoever, you could do this with any function. What's the effect of multiplying x by 2, multiplying x by 5? Sine of 2x versus sine of 5x. What is that doing? It's not just steeper, it's compressed. It's stretching in compression horizontally along the time axis. That also causes the more sine is compressed, the more steeper it gets. Sure, absolutely, that too. But I want you to think of this as an algebraic compression or stretching horizontally. What's the effect of multiplying the whole function? Y equals 2 times sine x. What did that do? That stretched vertically. Note the difference in your calculator. If you're not sure of this, check this. There's a big, big, big difference between 2 sine of x and sine of 2x. Graph it. Check it for yourself. 2 sine of x is tall and slow. Sine of 2x is short and short and wiggly. Check it. Two sine x versus sine of 2x. Very different functions. Incidentally, this means be very careful with your calculations. If you've got sine of 2 times x, you cannot solve for x by dividing by 2. Y'all see? Or have done algebra recently enough to know what I'm talking about? Okay, so if we multiply the independent variable, the inside, multiply the x by 2, that makes the ripples, the wiggles, the oscillations, the vibrations more, dare I say, frequent. The frequency increases. That's what this term comes from. The bigger the omega, the ripples are happening faster. If I double omega, the period halves. If I double omega, the frequency f itself doubles. However, omega is not quite the same thing as frequency f. Natural frequency, frequency, they're related, they are not identical. Natural frequency versus frequency. Natural frequency is off by a factor of 2 pi. Natural frequency omega is natural in that the equations, if you just write sine of 2x, sine of 2t, whatever, the 2, a single number in there, that is the natural frequency. If you're using a simple single frequency, a simple single formula, that which multiplies time, that's angular frequency. But that which multiplies time is not, in fact, the cycles per second. If you want to find how many cycles per second, the ordinary frequency, which y'all promised me earlier that you feel comfortable with, you take whatever multiplies your time variable and divide by 2 pi. So for instance, we just did the example of sine 2x. What is 2? Is that omega or is that f? And y equals sine of 2x. What's that 2 tell you? That's omega. If you got a simple formula, sine of 2x, that 2 is the omega. Use the formula, Luke. Calculate for me then the frequency. If you've got y equals sine of 2x, 2 is the omega, what's f? Plug it in. I do hope you are carrying along with your calculator here, or Desmos or something. When I plug in that example, the last example that I had you graph, y equals sine of 2x, If omega is 2, that means 2 over 2 pi. Frequency should be 1 over pi. 1/3 roughly. Or equivalently, period is 2 pi over 2 is roughly 3-ish pi. Hey, check on your calculator. Scan through. After pi seconds, after 3 seconds along the x-axis, is sine 2x going through about 1 full cycle? Do this experimentally. Do you all have graphed y equals sine 2x? Look at x equals roughly 3. Is that a full cycle? Egads. It's like I'm onto something. Sine of 2x has completed 1 full cycle, which defines period when x, or time, it's x in your calculator, but what does x represent? It's time. When time equals 2 pi over that which multiplies your x. Do you see what I'm leading up to here? I want you to understand the difference. No, not just I want you to. You must understand the difference between frequency, natural frequency, and period, and how to calculate one from the other. Let's do an example. I'm going to give you an example, a couple of examples. We'll start here. If I tell you that the Earth rings with a frequency of something like 54 minutes, I want you to calculate for me what is the frequency of this oscillation. Do this together, please. Calculate F. If I tell you period equals 54 minutes. Hey, pro tip here, by the way. What's a minute? Do we use minutes in physics? Step uno in problem solving physics 111, 112, convert to SI units. I shouldn't say 54 minutes. What should I say? You shouldn't calculate with 54. What should you use? Seconds. How many seconds in a minute? So how do you convert? Multiply by 60. I think that the period, I immediately look at this. If I were sitting in your shoes, if I were sitting in your seat, standing in your shoes, I would convert 54 minutes into 3240 seconds, 3,240 seconds. Okay, now if you know period in seconds, how do you get frequency? Did you get 1 over period equals frequency? You should. The correct answer is 0.00003. 0.00031 if you want to be more precise. 000? 000 would be 000. Did you do 1 divided by 3240? What did you do? Which is what? Yes, and then you did? You don't need to do that. Once you've got frequency and period, those are just reciprocals. You're doing extra steps. You found Yeah, you're doing extra steps there. Just take the reciprocal of 3240. Once you've got the period, frequency is just 1 over that. I think you found omega. Yes. That's not omega. If I say frequency, I just mean frequency, frequency. You're anticipating the next step. Okay, can you find the frequency? What's the frequency? Which is 0.0003, etc. Good. Okay. So step 2, find the natural frequency. What's omega? You have a head start on that. Hint, you've already found frequency. How do you get from cycles per second to radians per second? Okay, so if you've got the cycles per second f, I multiply f times 2 pi to get back to omega land. My answer for omega is 0.0019. Did you get 0.0019? Great. Graph that sucker. Do you know how to set, wait, hold on. Do you know how to set window? Zoom window. Your graphing window, second window. If you graph it and you don't know how to set your window, it's not going to look like anything at all. If you know how to set your window, graph y equals sine of 0.0019x and look at it. It is not linear. You need to set your window. Go up to zoom window and set it so that your maximum x value is something appropriate. Your maximum x value is, say, 3240, for instance. That'll show you 1 full cycle. Try it. That's not just for Selena's case, for everybody. If you don't know how to set your window, second window on a TI calculator, second, I think it's F3 on a TI calculator. I don't know Desmos command to do this, but on a TI calculator, second window lets you set your X range, your time range. If you just graph from 0 to 5 seconds, you're not going to see nothing on your calculator. Graph y equals sine of 0.0019x and set your window so the max x range is, for instance, 3240 seconds. If you set max x to 3240 and hit graph, you're going to see a very familiar looking face. Try it. Okay, so has everyone had a chance to see y equals sine x? And y equals sine something x. That something is the omega. You comfortable doing this? And are you comfortable seeing the connections between omega, f, and t? Give me questions. Squeak now or forever hold your pee. You may never urinate unless you ask me a question. No, or forever hold your peace. Sorry. You may never make war again unless you ask me a question. It's broken? Show me. Sure, that's reasonable. Graph it. What'd you put your vertical? Your x scale is fine. Your minimum y, your maximum y. Hold on a second. Oh, you didn't put an X.
Oh.
It's not sine of 0.0019. It's sine of 0.0019x. Do that. See if that gives you your result. Yeah. FYI, you shouldn't be plugging in sine of 0.0019. Your formula in your graphing calculator, if you're graphing the sucker to follow along, sine of 0.0019x. Makes a much more interesting pattern. So I think reasonable parameters might be x equals 0, x min to 0, x max to, well, what did we calculate the period before? 3240? 54 times 60? Look at that. Does that make a nice pretty sine graph with one full oscillation in that window? Are you doing sine of 0.0019 or are you doing sine of 0.0019x? And what are your x min and x max? What's your y min and y max? No. The height of sine x is not 3,240. The height of sine x is 1. Go from -1 to 1. Well, what is your amplitude on something on 1 sine x? Your amplitude is 1. Remember what the multiplier for sine is. That's the height. Your y scale going from -1 to +1. Yeah. Yeah, you see it? And look at the period of that cycle. When your cursor goes over to x equals 3240, you've gone through one full cycle. Just exactly the mathematical representation of what's going on the planet as a whole. Is that in fact right? When you scroll over, can you see at 3240, x equals 3240, you've gone through a full cycle? Anyone else want error debugging on your calculator? Or Desmos, but I'm better on the calculator. Did you get it, Mitzi? Great. Okay, so I've been referring to this. Let me introduce this formally, and I'm going to give an equation for him as well. Here's the spring oscillator. Oh, this is sideways from what I previously described. Everyone turn your head sideways. No, you don't have to turn your head sideways. It works either way! I'm going to give examples where the spring oscillator is on a horizontal frictionless surface. I'm going to give examples where the spring oscillator is vibrating up and down. Now, when the spring oscillator is going up and down, there's gravity too. Gravity is another force acting. If you've got a frictionless horizontal surface, gravity is not helping it spring back and forth. Which of these is going to be a harmonic oscillator? There's a constant function as well as a linear function in the vertical case. There's just a linear function in the horizontal case for the force, right? You see what I'm talking about? There's a force. There's one force in this example. There's two forces in the vertical case. As it happens, constant gravity cancels out. It doesn't end up having a significant effect on the period, on the frequency, on the angular frequency of a vertical spring oscillator. If you have a mass on a spring dangling vertically, it bounces up and down with exactly the same frequency, exactly the same period as if you laid the whole sucker on its side and had it springing backwards on a horizontal frictionless surface. The equilibrium, the unstretched length of the spring stretches if gravity is pulling it, versus sideways, the unstretched length of the spring will just be the unstretched length of the spring, but it has no effect on the sine wave parts of the equation. So I'm going to go back and forth between horizontal and vertical springs because the springy behavior, the oscillations, the vibrations, the simple harmonic motion is exactly the same in either case. Our example is, let me define it precisely, if we take a block of mass m on a horizontal frictionless surface or dangling in free space, attached via the spring of spring constant K to a fixed point. That's a horizontal subharmonic oscillator. You could do, I shouldn't even say it's more complex. There is an additional force, but the spoiler is, the amazing part is, that force of gravity does absolutely nothing to the oscillatory nature of the mass on the spring. Okay with that? Can I move on? I've described this like 3 times. You okay with me moving on past the words? These slides haven't been posted, by the way. I'm sorry. Again, I left my computer at home, but they will be. Okay, so I want to briefly review springs real fast. Spring equation, Kx. Well, okay, negative Kx. The negative reminds us that if I stretch the spring, the force compresses. If I compress the spring, the force is in the opposite of the compressive direction. That's what the minus sign tells us. K is the spring constant. Remember that? Not 9 times 10 to the 9. Do this as an example real fast. We're not going to talk about the oscillations. I just want you to remind yourself of what spring constant is. Suppose I've got a 1 kilo mass, and that gets the equilibrium length of the spring to 5.6 centimeters. Then I put a 1.3 kilo mass. How far does the spring stretch? I'm not talking oscillations here. If I just set it, dangle it, and that's where it goes, dangle the heavier thing, where does that go? Do you see what smell what I'm stepping in? Smell what I'm smoking? Check your neighbor. Go on. Experiences. Do you see? Or are you lost? Who's lost and who's done? Okay, here's how I would do this. What forces act on the spring? What forces act on the 1 kilo mass in the first case? Gravity and a spring. I mean, it says it's hung from a spring. So 2 forces, I'd say mg and kx act. If I say it's just hanging there, which of these is bigger? If it's just hanging there can't be a winner. If it's just hanging there, they must be in equilibrium. So how I would handle this is I'd say mg for 1 kilo, in other words, 9.8 newtons, mg, 1 times 9.8, equals 5.6 centimeters times your k. Solve for k. What do you get? I will do this on the board. And the people who are watching on Zoom are screwed. Projector, selecto docam. Come on, wake up. Here, boy. Come on. There we go. Okay. Yeah, well. My jokes are corny, so is my paper. There we go. Okay. Okay, so here's how I'd analyze this. I've got a 1 kilogram object, and the spring has stretched to 5.6 centimeters. I should be precise. The spring has stretched by 5.6 centimeters. I never told you its equilibrium length. How I would start to understand this is to say if it's just sitting there, the up force and the down force must balance. Kx equals mg. So I don't know K, but I gave you 5.6 centimeters. I know mass. God willing, you've been beaten into the fact that G is 9.8 long enough. I can use this. I can solve for K. How can I solve for K? Divide. This gives me a K of 175. What are the units? Kx equals newtons. So what's K? If K times x equals newtons, then it must be newtons per meter. There's your spring constant. That's the first thing. That's the knee-jerk reaction to saying stretches by 5.6 centimeters when there's a 1 kilo mass from it. Yeah? Okay, so now follow up here. If I replace the 1 kilo mass with 1.3 kilos, what happens? How does my spring constant change when I change the mass? It doesn't! That's why the spring constant is called the spring constant. So if I dangle this, now I've got an unknown stretch, and I've got still the idea that he's in equilibrium, kx equals mg. It's the same k. It's an unknown x, new m, g does not change. Solve for x. Mental math says that's 7.3 centimeters. 1.3 times 9.8 over 175, right? .073. Yeah? Am I right? Phew. I have been wrong before. I've been wrong before in front of you guys. I make goofs. Okay, so here is the magic. Here is the magic. Putting a bigger ball on the end stretches the equilibrium length, the balanced length of the spring further. But the magic is, if I wiggle this big heavy guy up and down, if I allow him to bounce, he will bounce in the exact same way as if I set the whole sucker on a table. Joink. Set the whole sucker on. Ooh, didn't mean to do that. I'm getting very excited and passionate about my lesson. If I set the whole sucker on a horizontal frictionless table, it bounces back and forth in exactly the same fashion. The equilibrium length is stretched. Gravity stretches the equilibrium. That doesn't touch the period, the amplitude, the frequency, the angular frequency, just where it starts, where its center is for the vertical case. Okay. I'm not going to make you do the entire equation with a center line being at a variable place and a sine wave superimposed on top of that. That's not too hard, but I want to keep things one step at a time for here. But the big reason we did this is so that you would remember what k means and how to use f equals kx here. That said, let me make it harder. Well, no, here. That said, let me give you this first. When you displace an object from its equilibrium position and the force pushes it back in what fashion, what gives you simple harmonic motion? Think about it, and then I want you to vote 1, 2, 3, or 4. Okay, everybody, give me the finger. Oh, correct answers. Or maybe you guys are French and telling me to fuck you. I don't know. Zwei Bier bitte. Yes, very good. 2 is the correct answer. Linear force gives rise to a sinusoidal motion. Yeah, you remember this? I only droned on about it for like 10 minutes earlier. Now, here is the capstone of today's lecture. Muy importante. Please listen up. The frequency for simple harmonic motion does not depend on the amplitude. The frequency depends on the thing that oscillates. I like to distinguish the oscillation from the oscillator. The oscillation is the waving, the pattern, the vibration. The oscillator is the thing that is being waved, vibrated, moved back and forth. Frequency for a simple harmonic oscillator doesn't depend on the wiggle, it depends on the wiggler. The wiggler. Oh my God, what is this just like? The capacitance of a capacitor doesn't depend on the electricity, it depends on the capacitor. The resistance of a resistor does not depend on the current or voltage, it depends on the properties of the resistor. Same thing here. For the spring oscillator, what determines K? What determines K for a spring oscillator? The spring. What determines M for the spring oscillator? The mass on the end of the spring. Does this change if I have a big or a little oscillation? No, it doesn't. Go to your supermarket tonight. Take a big stack of bananas and drop them from an inch above the surface of the spring scale, and then drop them from 3 inches above the surface of the spring scale. Then drop them from a millimeter above the surface of the spring scale. The vibrations, you get a big vibration, or a little teensy vibration. The little vibration will happen over a short distance, but a small velocity. The big vibrations will be moving fast velocity, but goes a further distance. The time will not change. The period, the frequency, the angular frequency will not vary if you have a big oscillation or a little oscillation. Little oscillation, short distance, slow. Big oscillations, big distance, but fast. The time will cancel out. Try it. Go to your supermarket and test it. Also, could you pick me up some milk because I'm out? Gallon of whole, please. I'm going to write this in terms of omega. You'll see the equations are always easiest. The equations always work out to be easiest with natural frequency. That's why natural frequency was discovered, invented, used this way. If you want to find frequency, how would you find frequency? If you know omega equals root k on m, how would you find f? Come on, you got omega. How do you get f? 1 over 2 pi times it. How would you get period if you've got omega? 2 pi over this much. Yeah. In your textbook, on the online resource, on YouTube videos, people will present 3 different equations. Square root k on m, 2 pi square root k on m, 2 pi square root m on k, as if they're 3 separate things to know. Blech! Gross. No. Don't do that. Don't do that to your brains. I strongly suggest learn the omega formula for every system we encounter here, and learn how to connect omega to period and frequency. And that is by far the simplest way of doing things. You are much more likely to screw things up if you try to memorize 16 different formulas. Keep it simple. Keep it simple. Know the connections, and it all gets really simple. Okay. Again, the big conceptual question I will ask on your midterm, final exam, is if I have twice as big an oscillation, is the period longer or shorter? What do you think? The frequency doesn't depend on the amplitude. Can the period? Where does amplitude play a role in this equation? Do you see an amplitude here? As the mean goes, is the amplitude in the room with you right now? No. A bigger amplitude does not have a faster or slower period. Bigger or smaller amplitude doesn't affect angular frequency. It doesn't affect frequency. It doesn't affect period. Bigger or bigger amplitude, smaller amplitude means the height of the oscillation is bigger. But what controls the period for an oscillator? It's the oscillator, not the oscillation. Go take your kid, or my kid. Yeah, actually, that's a great idea. Hey, free babysitting. Everyone, go take my kid to the playground. Give them a gentle push on the swing. Watch them swing back and forth. Give them a big push on the swing. Whee! Watch them swing back and forth now. Unless the kid falls off the swing or is pumping their legs, if they're acting like a simple pendulum, you'll see the big oscillation and the small oscillation both have the same time, to complete one cycle. The big oscillation, you're going fast, duh. You're going fast, but you have to go further. The small oscillation, you're always going slow, but you don't have that far to go. Time cancels out in either case. Try it yourself. Do you guys have playgrounds? Wait, does ASU West have a playground? That's a crime. Gosh darn it, you're an undergraduate. You're not in the nursing home. Why don't we have a playground here? What are we doing with your tuition dollars? Trust me, not very many of them go to me, I promise. Damn it. Okay, that's the other thing. Buy me 1 gallon of milk, take my kid to the playground, and write Michael Crow and demand a playground on West Campus, okay? We're not quite done. We're almost done. Wait, are we done? No. Okay, I've got a couple minutes left. Let's talk about kinematics real briefly. I need you to remember what kx is, and I also need you to remember a little bit about velocity and position. Velocity is the slope, velocity is the rate of change of position as time passes. Velocity is the slope of a position graph. Acceleration is the rate of change of velocity, which is to say, I don't know, Selena and, wait, is Selena the only one who didn't have me? Who else didn't have me last term? You didn't have me. You didn't have me. You didn't have me. Lots of people didn't have me. Okay. Did your instructors tell you this? You can see accelerations on a position graph if you look at the curviness of the graph. Did they tell you that? Did they tell you that? If you've got a line on a graph, that is zero curvature. If you've got a line which is bending this way, that way, or the other way, that's curved. That is a changing slope. That's how you see acceleration on that graph. So take a looky here. Okay, I want to be able to point. Here we go. If I stand away from it a little bit, my shadow. Okay, take a look at it up here. Right here, this part of the graph, this part of the graph. Oh, hey, actually look, the shadow of my pencil really lies under this. Is this a line? This is a linear part of the graph, right? Look, my pencil, my pen can almost be that part of the graph. This is a part where curvature is very small. There's very little acceleration at the zero crossings. When position is close to its origin, when x is close to 0, what is the force of a spring? What is kx when x is small? It's small. Oh my God, there's not much force when a spring oscillator is close to its origin. There's not much force, there's not F equals ma, there's not much acceleration. No wonder there's no big curvature. There's no big acceleration when F equals kx equals ma equals 0. But, what about when we are accelerating a lot? Well, here, look, I have a very large value of acceleration. Notice my slope is changing rapidly around the extreme points of the graph. When my position is far away from 0, when I am at the max and minimum extents of the sine wave, F equals kx is big, right? Because x is big or small. And if force is big, isn't acceleration big? And acceleration is the curvature of a position graph. Looky, looky, I see curvature when I'm far from 0. It's all together, man. It's all one big thing. Also wear tin foil or they'll read your mind. Okay, so, I want you to be able to look at a position time graph again and not just see, oh, look, a wiggle, but I want you to see, look, there is a big negative velocity here. And the velocity is large because the slope is steep and negative, but there's not much acceleration. There's not much acceleration because the slope is like a line. Whereas over here, look, hell, at this time there is 0 slope. The slope is at this instant 0. At the peak of your motion, you ain't moving. Your velocity is 0 at your furthest extent. At the highest point of the swing, you're not going up, you're not going down. But there is a big acceleration. Your velocity is rapidly changing. Do you see that? Almost done. When your displacement is 0, it's at the equilibrium. at the equilibrium point, tell me about your speed and tell me about your acceleration. I just showed you the answer on the previous. Can you put that, can you apply what I just said here? When the displacement is 0 at equilibrium, what is the speed at equilibrium and what is the acceleration at the equilibrium position? Okay, let's go back. Take a look. Here's the equilibrium position. When x equals 0, when position equals 0, we are passing through 0. Can you tell me about the speed? Is it big? Is it little? Shoink, 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 shoink. Is it accelerating? Well, it's got to be either moving or accelerating. If it's not moving and it's not accelerating, then nothing's going to happen. I see a steep slope when I'm passing through 0. What does the slope of position tell us? There's a big speed. Your speed is maximum. What about your acceleration? Are we curving? Your acceleration at that instant is 0. The correct answer here is maximum and 0. First one is correct. Hey, we're going to continue getting wiggly with it for another, oh, that's a terrible phrase. I apologize, and I will not say that again. We are going to continue oscillating back and forth and hopefully oscillate a little bit forwards in your understanding as time goes by. I will see you all on Wednesday, hopefully with an iPad.